In this video, we are going to talk about non-singular matrices. We'll start with some definitions, and we'll start right off with the definition of a non-singular matrix. We say that an n by n matrix, let's call it A, is non-singular if the only solution to this linear system where A is the coefficient matrix and 0 is the constant vector, in other words, this homogeneous system, is the trivial solution. Remember that the trivial solution is the set containing the 0 vector. So if the trivial solution is the only solution to this linear system, this homogeneous system, then the matrix is non-singular. If it's not non-singular, it's singular. So these words are opposites of each other. So every n by n matrix, we call n by n matrices square often, is either non-singular or singular. Then we define the identity matrix. Again, only square matrices, or all identity matrices are square, n by n. It's the n by n matrix with ones on the main diagonal and zeros for all the other entries. So later we'll have a more formal definition of the identity matrix, but this one will do for now. And we can illustrate this definition with some examples. So here's the 2 by 2 identity. The main diagonal is from the top left down to the bottom right. So here's a 3 by 3 identity, the 4 by 4. And so we can see that all these other non-diagonal entries are zeros. So it's easy to identify an identity matrix when you see one. All right, so now that we have those definitions, the main theorem, the only theorem that we're going to look at in this video is what I'm calling the non-singular matrix properties theorem. There's a different name for it in the textbook. And it's an equivalence theorem. That means that these four statements are logically equivalent. And that means that they are either all true or all false. So if A is an n by n matrix, so again, we're only talking about square matrices, 2 by 2, 3 by 3, 4 by 4, etc. These statements are logically equivalent. A is non-singular. Okay, so if A is non-singular, then these other things are true. If A is not non-singular, if A is singular, then these other things are also false. So what are the other things? It's A is row equivalent to the n by n identity matrix. The null space of A, remember this notation, that's the null space of A, is equal to the set containing the 0 vector. And the system, LSAB, in other words, the system with A as the coefficient matrix and B as any vector in Cn, has a unique solution. It has a unique solution for every B in Cn. Now this fourth statement is probably the most complicated one. So let's break it down a little bit. It says a few different things actually. First of all, it says that this system is consistent. So the fact that it has a solution, that means the system is consistent. More specifically, that solution is unique. So the existence uniqueness theorem tells us that every system is either consistent or inconsistent, and then if it's consistent, it either has a unique solution or infinitely many solutions. So this statement narrows it down to consistent with a unique solution for every B in Cn, and that's also important. In other words, it doesn't matter what B is. If B is any column vector in Cn, so if A is, say, 3 by 3, this would be C3, then this system has a unique solution. Doesn't matter what the entries in the vector B are, we know that the system has a unique solution. I won't go through the details of the proof, although that's a useful exercise, both to learn how to do proofs and also to understand why this theorem is true. I'll just point out that because it's an equivalence theorem, these are all if and only if statements. In other words, 1 is true if and only if 2, 3, and 4 are true, etc. So the way I've done the proof here is sort of typical, where I start with one of them. In this case, the first one, if A is non-singular, well then that implies the other three, and then you have to make a connection back to A, back to number one rather, so that they all imply each other. And then you have to show the converse as well, because if and only if statement. So if one is true, they're all true, and at least one of these implies one. So you get this connection. And then if one is false, they're all false. And if one of these is false, that implies that one is false. And that's what this second paragraph says. All right, we're going to focus on using the theorem. We'll do a few examples. So first, here's a matrix A and a vector B. We see that A is a 2 by 2 matrix, B is a vector, and C2. And we're asked to find the null space of A, and then we're asked if A is singular or non-singular. And then we're asked, is this linear system with A as the coefficient matrix and B as the constant vector, if that is consistent? Well, theorem 2.1 is really useful to answer all of these questions and other questions as well, as we'll see. And really all we have to do is apply this second statement. A is row equivalent to the n by n identity matrix. In this case, n equals 2 because A is 2 by 2. And so we row reduce A. Remember that symbol is the row equivalent symbol. So you do this on your calculator or on a computer, and or you could even do it by hand, and you'll see that the RREF, the row reduced echelon form of A, is indeed equal to this matrix, which we can identify as the 2 by 2 identity back from our definitions. Okay, so we know that statement 2 is true. Okay, this is true for this example 2.1. Well, that means all the other statements are also true. Okay, and in particular, we can answer these questions using the results of the theorem. So find the null space. Well, it's very convenient that the third statement in the theorem tells us the null space is the set containing the zero vector. So we get that sort of for free, if you will. Is A singular or non-singular? Well, A is non-singular because it row reduces to the identity, and that's the first statement in the theorem. Is the system consistent? And we're given this vector. Well, if we didn't want to use the theorem, we could row reduce the augmented matrix like this and see whatever we get. And if we, we'd get a matrix with 3 columns, and if there's not a pivot in the last column here, the existence uniqueness theorem tells us that this system then is consistent. But statement 4 here, as we just discussed, tells us that if these other statements are true, then the system has a unique solution. In other words, it is consistent for every B and Cn. Well, n here is 2, and here's a vector in C2. It doesn't matter what these numbers are. We could put any numbers we want in here. We know that this system is going to be consistent by the fourth statement of the theorem. So yes, that is, the system is consistent, and yes, A is non-singular, and the null space of A is the set containing the zero vector. Now, this question is a little bit contrived in the sense that this example, if you will, because these questions are specifically based on the theorem here. We could ask some other question about A that theorem wouldn't answer. So we'd have to use some other technique, some other way to decide. Later we'll talk about different properties that matrices can have in module 3, and we might ask if A is Hermitian or something like that, and the theorem 2.1 won't tell us that. But part of the key to answering questions in this class is to figure out what theorem or properties um, do I use to answer the questions. And once we figure that out, it's often pretty simple. In other words, when you're asked about the null space of an n by n matrix, in particular when you see these words singular or non-singular, this non-singular matrix properties theorem is a really good theorem to check. In other words, see if any of these things are helpful and will answer any of the questions. It might answer all of them, it might answer some of them or none of them, but it's at least worth checking out. Okay, so let's do another example. Determine if the following statements about the matrix A are true or false. So here's a matrix A. We have a 3 by 3 matrix in this case. We have a bunch of statements about it. And there's a longer discussion here of how to go through this, but let's just stay up here and we'll look at A and just go through one by one. All we have to do is row reduce A. So here's A, we put it into a calculator or a computer, it row reduces to the 3 by 3 identity. So every statement in theorem 2.1 is true. Let's see how many of these we can answer using theorem 2.1. And so we don't have to keep switching back and forth between pages. It might be useful just to summarize it here. So A is singular. A is row equivalent to the identity matrix. The null space of A is the set containing the 0 vector. And summarize this. We'll just say LS A B is consistent. Actually, we can be more specific than that, right? Has a unique solution. For every B in this case, C3, because A is 3 by 3. All right, so let's see what these 4 things will tell us about these statements. Well, first of all, because A is row equivalent to the identity, that means number 2 is true. That means all of these are true. Okay, well, that means A is singular. Oops, I have that backwards. A is non-singular. Okay, there we go. A is non-singular, so that means this is true. A is singular. Well, that's false. And that's really easy if you understand the definition of singular and non-singular. Although if you don't, and it might be a little confusing, you might think, well, why would they ask me about both of these things if it's that simple? Well, just to check to see if you know what you're talking about. So this is a really easy, these two are very easy if you understand the definition of non-singular and singular. In other words, if A is a square matrix, so we know it's 3 by 3, it's square, one of these has to be true, and then by definition, the other one has to be false. So if you figure out one of these, you get the other one for free. If I figure out that A is true, that means B has to be false. A is row equivalent to the 3 by 3 identity. Well, yeah, that's true. We just figured that out. The null space of A is the empty set. That's true. That's statement 3. Let's see. The null space contains only the trivial solution. Okay, well, we have to do a little translation here. What's the trivial solution? The trivial solution is the set containing the 0 vector. So again, it comes down to definitions. Do you know what the definition of the trivial solution is? Well, if you do, the null space contains only the trivial solution. Well, the trivial solution is the 0 vector. So yes, that's true. The system has a unique solution for every B and C. Well, that's just a quote of statement 4. So, yep, that's true. And the null space contains infinitely many vectors. Well, we just found that D is true. So here's the null space, and there's only one vector in there. So D and G are, they can't both be true. If D is true, G is false. If G is true, D is false. And in particular, since D is true, we know G has to be false. Okay, so this is a pretty typical example of a question in a linear algebra class where the math, sometimes people say, this is the only math, and then the rest of this is just, logic or something. Well, math is logic, but I understand this is what people mean. This is the only computation we have to do. It's very simple, and we just do it on a calculator, computer. And then we draw conclusions from this one simple computation. This is a pretty hard question because it involves logical implications from a theorem that has, all these terms and symbols, and we have to understand what all these things mean. All of that is to underscore, when we see definitions, if you're in a calculus class or something, a lot of times we just kind of gloss over definitions, or there's a temptation to, because you focus on the computations, find the derivative of a function or solve some story problem. And the definitions are not anything we pay a lot of attention to, maybe. Likewise, theorems, you remember maybe the mean value theorem from calculus, it's so important, but we use it to prove other theorems, and then we use, those theorems to solve problems. But in this class, the theorems are the formulas, if you will. Sometimes people say, well, what formula should I use to solve this or that? Well, in a linear algebra class, there aren't very many formulas. There are many theorems, and we use the theorem kind of like we would use a formula, say, in a calculus class. And because theorems are full of, new symbols and words, and that the words have definitions, you just have to make sure that you understand what all the symbols mean and what all the definitions mean. And so, look those things up. You're not expected to memorize all this stuff. Okay. But once you do that, then it's a matter of just sort of matching. And if you understand all the definitions and the symbols, these questions are almost embarrassingly easy. Okay, let's do one more. And this one is a little shorter in the solution here in the notes, because we've done a couple of these already. Same thing, here's a matrix A, and it's the exact same statements here, the same 7 statements, A through G, and we want to find out which ones are true and false. Same thing, we just row reduce A. Now notice, in this case, A does not row reduce to the 3x3 identity. Okay, so what does that mean? That means that all the statements in theorem 2.1 are false. Okay, so let's just go get this little summary that we had, and we'll bring it over here. So these are all false. All these statements are false. Now you have to be careful what it means for a statement to be false. Sometimes that tells us that something is true. Sometimes it doesn't. For example, let's just pick, say, number 3. Number 3 is false. So that means that the null space is not equal to the set containing the 0 vector. Okay, well, that gives us some information, but if we wanted to know what is the null space then, well, we know what it isn't, but there are a lot of other possibilities about what it is. We know, because of the existence uniqueness theorem, that the null space has infinitely many solutions in it, because homogeneous systems are always consistent. We have a theorem that tells us that. The null space, by definition, is the solution set to LS0. Okay, and that homogeneous system is consistent, and it will always have the trivial solution. But because this is false, that means that there are other vectors inside here the zero vectors in there, but then there's going to be a whole bunch of others, and the existence uniqueness theorem tells us that there are in fact infinitely many others. Well, to find out what those other vectors are, we actually have to solve the homogeneous system. That's not a hard thing to do. We learned how to do that in previous video. So if I wanted to know what the null space is equal to, I would have to do some more work. I don't know what it is just by doing this little computation. But I do know that it's not equal to this, and I do know, for example, that the null space contains infinitely many vectors. I know that that's true by a combination of theorem 2.1 and the existence uniqueness theorem. Okay, so we can just go through these one at a time. A is non-singular. Well, that's false. A is false, so that's false, and then B is true because these are opposites. So A is singular. A is row equivalent to the 3 by 3 identity. Well, no, it's not. That's false. The null space is equal to the set containing the zero vector. Well, that's of course false as well, because all these are false. The null space contains only the trivial solution. Oh, notice D and E are the same thing, just written in a different way. This is the set that contains only the trivial solution. So that's false. So E is also false. This system has a unique solution for, well, no, that's false. Okay, so, and the null space contains infinitely many vectors. That we found is true, and that's probably the most complicated one to figure out because 3 is false, and the existence uniqueness theorem gives us extra information to tell us the only alternative, if 3 is false, is that there are infinitely many vectors in the null space. In other words, it is not possible that the null space is the empty set because every homogeneous system has the trivial solution, so the solution set is never empty. Okay, and that's all summarized here in the notes. So that is some information about non-singular matrices that will be very helpful going forward.